Thank you. I want to commend all the speakers today. I've really enjoyed listening to all of them. I'm not going to talk about sediment at all. You know, I think Satish made most of the points that I'm going to make, and I'm going to make them perhaps in maybe a more simple-minded way, or a simple-minded way. And that is that the hydrology of our landscape is a complicated, there's a complicated set of factors that all come together to create what we now observe as our hydrology. And so that's what I want to talk about today. I'm not going to talk about sediment. I am going to talk a little bit about drainage and some of the other factors I think that come into play to give us what we have now, what we experience now on our landscape. Again, starting with a general discussion here of agricultural water management in general, before I pick on drainage specifically, you can put yourself down on any place on the planet, and if you're trying to grow something, you've got a certain precipitation pattern that you have to deal with. Mother Nature gives you only so much water, and it gives you that over a certain schedule over the year. And if we look at, take any place, any location on the planet, you know, the native vegetation, wherever you might be, it tends to match up pretty well. The consumptive use of native vegetation with the natural rainfall matches pretty well. As soon as you uproot that native vegetation and try to grow something else, typically displacing a perennial vegetation with an annual vegetation, now you have a consumptive water curve that looks something like this. And these are generic, okay? Could be corn, could be soybeans, it could be wheat. But those curves often don't match up very well. And again, I've seen this all over the world where I've worked. We're always dealing with situations of excess water or deficit water. And where water comes to us more quickly than we need it, coupled with soils that don't drain very well, it sets up a scenario for drainage needs. And that's what we experience in the upper Midwest, throughout Europe, and many other places in the world. Where our crops need more water than Mother Nature is giving us, it sets up a scenario for having to supply more water to that crop. Couple that with soils that don't store a lot of water, sandier soils, and you set yourself up for some significant irrigation endeavors. If we look at agricultural water management and look at the United States and look at all the arable land in the United States, depending on whose estimate you look at, the amount of, the percent of those acres that require artificial drainage are pretty significant, on the order of 25% when we consider both surface and subsurface drainage or tile drainage. And the acres in tile drainage, the 9% there, shows up as a pretty significant dot as well. What do you think the percentage of acres looks like on the irrigation side of things? Bigger. You'd think really big. Well, there's irrigation. And it's really sort of along the same playing field there as tile drainage. Worldwide, about 25% of our agricultural soils need and require artificial drainage. A great percent require irrigation as well. And we all know very well that most of these soils are some of the most productive soils that we farm when we're able to manage water. And all of you know much better than I do that when it comes to farming, water and dealing with water is sort of the front lines of what we have to deal with in terms of Mother Nature. So again, now just focusing in, getting away from irrigation, looking at drainage. This is an old map, but we used to ask agricultural drainage questions on the ag census that comes out, and that's not been asked for quite a while. It's going to be, we've managed to get a couple new questions in for the next census in 2012 related to drainage. So this is an old map, but the footprint probably looks pretty similar, even though the percentages have gone up from what we see here. But I think the interesting thing from this map is that we're doing drainage everywhere in the country. And this is, you see information at the county level here. And there are only very few counties that show up as not reporting any drainage at all as of the 1978 census. And of course, the area in the upper Midwest here is primarily where the practice of subsurface drainage, tile drainage is very prominent. So we're doing drainage everywhere. It's a very important practice. We've talked about hydrology all throughout the day, and I'll use that word a little bit too. But when we talk about hydrology, we're really just talking about the water cycle, the water balance. Hydrology is the study of that balance and what influences it. And prominent in that cycle and things that I'll mention here are ET, evapotranspiration, surface runoff, precipitation, and infiltration and seepage. So the big question, First, agricultural water management in general. Does it affect hydrology and stream flow? What do you think? Of course it does. If I were from Texas like Gary, I'd probably say, hell yeah, it does. It really does. We know over the course of human history, civilizations have failed because of mismanagement of agricultural water and the hydrologic impacts. Increased levels of salinity, rising water tables, and so forth. So entire civilizations have come and gone because of hydrologic impacts of water management. So yes, agricultural water management does impact hydrology and stream flow. What about agricultural drainage and its effect on hydrology and stream flow? First, just the general question, does it affect hydrology and stream flow? What do you think? A lot of heads nodding. Of course it does. Of course it does. This particular topic, agricultural drainage and stream flow, hydrology, flooding, there's literature going back at least 100 years on this topic. So the scientific community has been engaged in this particular area for a long, long time. There are some studies that I could point you to that would enlighten us all about some of the factors that come into play. But yes, agricultural drainage affects stream flow. But the more difficult question is, that we'll get to in a second, is as we look at Minnesota, of course, the blue areas here highlight all the channelized streams and ditches, not all of them, but most of them in the state. You know, more than 21,000 miles of those features, all the subsurface drainage features. So of course, no one in their right mind would suggest, could believe, I don't think, that all of this drainage activity in our state and throughout the upper Midwest doesn't affect hydrology. Of course it does. But do we understand precisely how it affects hydrology in all times, in all places, in all situations? Do we know how it affects hydrology? And I'm going to tell you that we don't really understand that. And the rest of my presentation is going to talk about why we don't really understand and can't answer this question specifically. How exactly does agricultural drainage affect stream flow and hydrology? There's some things we know, there's some things we don't know. And again, the overall message is going to be it's kind of a complicated world, and that's what makes answering that question so difficult. So why don't we understand it? Because there are lots of other factors that come into play. Lots of other factors. And the combined effects of those factors make it a very challenging question to answer. So what are some of these other factors? What else affects hydrology and stream flow in addition to agricultural drainage? Well, there's a whole list, and we've been talking about them today. Land use changes. The scale of observation. What are we observing? The field, the river, and so forth. We'll get into some of these. Rainfall. Dr. Seeley and others have talked about all the different characteristics of rainfall and how that's factoring into how water moves across the landscape now. The type of drainage. I've been using agricultural drainage as a general term, but guess what? There are different types of drainage, and they behave differently. Soil moisture status, water table status, and lots of other factors. Okay, and so I want to talk about just a few of these here in the next 2 or 3 hours. So the river here is then the great integrator of all these factors. You know, you stand any place on the river and you're seeing the culmination or the cumulative effects of all of these activities on the landscape. And so when you hear statements like agricultural drainage is what's causing all of that bluff and bank erosion, I think you have to step back. Hopefully you'll step back after today and say, you know, it's one of those factors, but there are many other factors that contribute, and we need to learn a lot more. So let's go for a few examples here. Let's take what seem to me as maybe some of the more straightforward ones. Let's look at the type of drainage. And I've mentioned some of these already. Think about surface drainage, ditches, and tile drainage. And I've kind of cast these on two different sides of the slide here with the subsurface drainage on the right. Contrasting these two things, surface drainage and tile drainage. Surface drainage tends to decrease infiltration. It gets water off the ground surface more quickly and reduces soil water storage. Tile drainage, in general, does the opposite. It tends to increase infiltration, increasing soil water storage and lowering the water table. Surface drainage tends to increase the volume and timing and rate of surface runoff, whereas tile drainage in general tends to reduce those things, tends to reduce surface runoff volumes and times. And it tends to spread the hydrograph out and spreads water yields from the field over greater amount of time. So now here we just isolating this one factor, the type of drainage. We've got all the surface drainage, whatever it is, 20, 30,000 miles of ditches and streams. We've got millions of feet of tile drainage. Who knows how many feet we have in this state. And as we've just seen, they're kind of working opposite of each other in terms of how they work hydrologically on the landscape. So then I would ask you, what's the sum total effect of all of that drainage? I don't know, because they work in different ways. It makes it a difficult question to answer. So here's a study that helps illustrate a little bit. Now this was a study in Oregon. It wasn't my work, I'm just pulling from the literature here, but they had 2 small watersheds, and that's what you see. The pink line is the smaller watershed and the dotted line is the larger watershed, and this is the surface water that they measured over a couple of storm events from those 2 watersheds. Then what they did is they went in and they tiled. They put subsurface drainage in watershed 2 and then measured the surface and subsurface water from that field. And that's what we see here now is the top line on the dotted line on the top, that's the one watershed. And now here's the response from the tiled watershed. And now we have 2 signals. We have the surface water and the subsurface water. Totally changes the hydrology of this smaller watershed here. When we think about the previous slide, where even though the watershed was smaller, it was sort of a mirror image of that of the larger watershed. But now that it's tiled, that signature is quite different. So again, just an example to show us how, again, the 2 different types of drainage work differently and make it challenging to understand the cumulative impacts on the landscape. How about some more examples? Land use change. We've talked about this a bunch already. I've got a couple of other examples here, and I'm not a scholar of land use change and so forth as some of our other speakers, but here's some interesting images I borrowed from a colleague in Iowa State. Here's a picture of a landscape pre-drainage, probably just after settlement here around 1900, and you see how heterogeneous this landscape is. You got a lot of wet hay acres, very few cultivated acres in that landscape. I pulled this quote out of the 1938 Yearbook of Agriculture. Haswell was an agricultural engineer, and so an interesting quote there. The first I had seen it that said that related sort of the advent of more increased subsurface drainage with mechanization. And it makes sense. I haven't done enough reading to know that that I can substantiate that any further. I'd be interested in knowing what your cultural histories and your families are telling you about some of those first drains that were put in on the landscape. But I thought that was fascinating to see that the age of mechanization had something to do with our thinking about water management as well. But here's that same farm now post-drainage, or at least the first crack at drainage on the landscape. And these are what we would call targeted drains or random drains. They were all hand-dug clay tiles, I'm sure. And so after those drains were put in, there's what the subsequent farm plan looked like. And now things are looking more organized. I can be a little more, I can plan a little bit better what I want that landscape to look like. We also see an increase in cultivated acres. Of course, that landscape today looks like this. And so many factors coming together to create that image we see now. Again, talking about this topic of land use change, thinking about the prairie, thinking today about our annual crops. And this is a study, again, just showing those water consumption rates, comparing prairie with our annual crops. And we all know it. The prairie, it wakes up earlier, it starts transpiring and using water sooner than our annual crops, and it continues later in the fall. What that does then is it changes the cycle of soil, water, moisture as it changes over the year. It impacts that. Of course, we also know that our annual crops oftentimes will out consume water that would be used by the prairie in the middle of the season. So here's another illustration of that same factor, or that same issue. Prairie versus corn. This is a study that comes out of Wisconsin. I want you to look at these curves. This is over about a 3-year period. That green line that just showed up, that's the cumulative evapotranspiration from prairie versus corn. Those lines look pretty similar. So even though the schedule or what's the word I'm looking for? Anyway, the way it plays out over the year ET, even though that's different, cumulatively speaking, they're pretty similar. But look at the drainage curve on the two. So that's the water that's lost through the bottom of the soil profile, and that is impacted significantly by those two different plant materials. The other thing to recognize here is the soil moisture status now. And so we have a much smoother line when we look at the prairie, much more, we have a wetter soil profile, and it changes a lot less over time compared with the corn. So the reason for showing this is not to suggest that we need to dial back our landscape to the prairie, only to show that as we look at the river today, it's the culmination of a lot of changes over time that have occurred. Scale of observation is incredibly important, and in terms of understanding the hydrology of the landscape. And again, another big factor in why it makes it very difficult to answer that question, how drainage is affecting hydrology. Reference condition, and we've heard about some of this already. If we think about the way our landscape has transitioned from the prairie, pre-settlement, to some land conversion with agriculture, to improved surface drainage and more intensification of agriculture, and now with what we experience today of maybe improved subsurface drainage, a lot of pattern tiling and so forth. When you get into a discussion about the hydrology of the landscape with your colleague or whoever it might be, and you start saying, you know, I think drainage has this impact or crops have that impact, you need to clarify right up front, what two conditions are you comparing? So again, if we talk about prairie to modern day, that's one comparison, and we can draw some knowledge from that. But oftentimes, you and I are starting at we're talking about different time frames and different reference conditions. So we need to clear that up right away. The spatial scale, where we observe water flow and hydrology, makes a big difference. Going from the edge of the field up to the basin. If you're standing up here right up there in the field, looking at water leaving the field from the edge of the field, is it going to look the same as if you're standing down here at the, let's say, the second or third order stream? Do you see the same hydrographic signature? No, you don't. Things change as you scale up from the field to the river scale. Everything gets more complicated. The soils become more complex and more diverse. Rainfall now is not occurring on just a field, but it's spread out over the landscape. And many other things change as you go up in scale. And oftentimes in research, we study some of these processes very intensively at the field scale because we can kind of get our arms around that. And both economically and physically, we can kind of understand how things work at the field scale. But the questions we're answering and the questions society is asking are at larger scales, and that's where things get much more difficult. Here's a study that provides kind of an example of what happens as we go from small scale to large scale. Now this is a modeling study, but it goes from a small portion of a field, 20 acres, up to a 24 square mile watershed. And this is a modeling study where they took sort of a conventional agricultural system that had good surface drainage, and then they compared that with the same system, but now with extensive subsurface drainage. At the field scale, we see quite a bit of difference between those two systems. Look at the top line here, the conventional system, and then the pink line, the improved system with subsurface drainage. As we go up in scale, watch what happens now. The curves start coming closer together, even closer together, and spreading out over time. And so as you dial it up to larger and larger scales now, it's going to be more and more difficult to tell the difference between those two water management practices. Even though they're fundamentally different at the field scale, we have very significant differences. But as we go up to larger and larger scales, it's harder to see and measure those differences. And that's the point here. Things shift as we shift in time with larger scales, and we see that attenuation. Rainfall characteristics, I probably don't need to say much about this after Mark Seeley's presentation today, but let's just pick on one particular element of rainfall. Think about a light, low-intensity rainfall compared to a very heavy rainfall. And we're hearing now we're getting more and more of these intensive rainfall events. But let's compare these two in terms of how a drainage system works. In a gentle rainfall event, it favors infiltration. Rain comes gently at rates lower than the infiltration rates of our soil, so that water can get into the ground. Intense rainfall event favors surface runoff. The rainfall comes faster than it can soak into the ground, and we lose it by surface runoff. A gentle rainfall event, the tile drainage system is going to sort of influence the flow of that system. Most of that water is going to get into the ground and through the tile. For the intensive rainfall event, even though the tile system is there, it never has a chance to get there. So the surface drainage features on the landscape are controlling what's going on in terms of hydrology. So there we have the same landscape, the same drainage, surface and subsurface, and guess what? Because we had a different type of rainfall event, the hydrology is different. So again, makes it very challenging to make these very broad general statements about how the landscape performs. So again, the general rainfall event, the surface drainage system is kind of out of the picture. The intense rainfall event, the tile drainage system is really pretty much out of the picture. So has anyone managed to sort of untangle this web of complex factors that determine our hydrology and stream flow? Not completely, but we're still trying, and we're going to keep trying. We had a researcher a few years ago, Kristen Bland, who put together an extremely comprehensive literature review. She pulled together a couple thousand studies, ended up with about 500 studies actually cited in the paper, trying to sort of boil down the effects of agricultural drainage on the aquatic communities. And one thing that Kristen found out, and she illustrates in her paper, is that, again, it's a complicated world out there, and everything is kind of connected to everything else in the ecosystem. So it makes it very difficult to make broad, generalized statements about what's going on. So in summary, we have significantly altered our landscape. There's no question about that. The impacts of that alteration are physical, they're biological, they're chemical, other types of impacts as well. The impacts on all of the ways we have altered the landscape depend on a combination of many, many factors. Land use changes, the scale of our observation, or where we're looking for these factors, for these impacts, rainfall characteristics, current soil and water table conditions that I didn't even provide examples on, the type of drainage, and it's extremely difficult to separate these factors. Making credible statements of impact must begin with defining all of those factors first. So if you're going to make a big general statement, make sure you say what the scale of observation is, where you are on the landscape, what the precipitation event is, what the antecedent conditions are leading up to, and so forth. So all of that has to be defined if you're going to make some statements about impact. And broad statements are problematic. And I'll just finish here with an image from, I guess maybe this could be looked at as sort of the next generation of drainage on the landscape. This is a picture of a pilot project. It's a two-stage ditch. It's an attempt at sort of building a little more Mother Nature into our traditional agricultural drainage ditches. And if you haven't had a chance to look at this one, you might want to stop out and check it out. But what it does is then it builds a two-stage ditch, builds a bit of a floodplain into the ditch itself. You know, typically the agricultural drainage ditch is a very steep ditch, and we have to throw a lot of money at them to keep them maintained and working well. So the two-stage ditch, again, it builds a floodplain down here in the ditch. This carries the frequent flows. The larger flows flow up over this floodplain. They slow down. They drop sediment. Denitrification takes place, and so forth. And this is one of a whole package of practices that are getting a lot of press now in terms of as far as dealing with the hydrologic and the water quality impacts of drainage on the landscape. I'll stop there, and if there's some time for questions, I'll be happy to.
We have time for a question or two, if someone has one or more. I have one, Dr. Sands. What's your perspective on the blind intakes from the standpoint of sediment issuing into the drainage stream?
Question is, what's my perspective on blind intakes, the gravel or the rock intakes? There's been quite a bit of work done on those. And first of all, what we find, both with the blind intakes and with the use of the riser, with the slotted riser, the Hickenbottom riser, is you do get some detention period where material settles out before it gets to flow down into the intake. And that percentage of settling is larger than most of us realize before doing the work. But the rock intakes, the blind intakes, they do work, they do function hydraulically. There are contractors that have been putting them in for many years. They do provide some water quality benefits, but the jury is kind of still out in terms of how long those water quality benefits will last. Some studies suggest that they might last 10 or 15 years. Other studies suggest that even if they start to fill up with sediment and don't continue to trap sediment, they will continue to function hydraulically and perform the water management goal and objective. So we're seeing hundreds of them go in on the landscape, and I would much rather see one of those than an open intake. But in terms of is it any better than a slotted riser, I think the jury's still out on that.
We have several, and I've been a bit concerned about what happens in 10 years or 20 years or whatever when sediment presumably fills a lot.
Yeah, it's a potential issue.
Question is,
is there any way to make that cost efficient? What you're just showing on the screen now, it looks like it'd be a very expensive project.
Yeah, I think that would be probably most of your first impression of this would be an expensive undertaking, and it certainly is. This one is so early on looking at two-stage ditches. Right now we're just trying to sort of determine, we're trying to quantify, the benefits and how they really work. In terms of the whole sort of socioeconomic picture, it's going to be a challenging one. So I don't have a lot to share there. Obviously, you've got a bigger right-of-way. If we can get some credits for part of that right-of-way, maybe the buffer that's required, if maybe that can factor into this somehow and reduce that overall, that overall right-of-way, that might help us. To state that a different way, if we also had to add on our buffers on either side of that, that might be very challenging. But perhaps there are some ways to think creatively about what we're doing with the buffers and maybe get some buffer credit for what's going on in the floodplain inside the ditch. It's going to be challenging. There's no doubt.
question over there.
Gary, up in the Red River Basin, they've had to go at drainage with at a watershed scale because of the volumes. And it appears that we're having these kinds of problems now at the Minnesota River, that we should start thinking in terms of watershed scale in planning hydrologic retention, whether it's culvert sizing or two-stage ditches. Have you got any observations along those lines?
Observations about whether we should do a plan on a watershed basis, or
perhaps we could go about planning at a watershed scale for some of our drainage issues in Minnesota.
Could you repeat the question?
yeah. So how should we go about planning at a watershed scale? Some of these drainage developments in drainage and drainage alternatives, and I think it makes a lot of sense to think on a watershed scale. I don't know if we necessarily understand how things work at a watershed scale as we look at some of these drainage features, but certainly I think anything more integrated in that way, there's probably going to be more power in that than sort of approaching things on a farm-by-farm basis. But it's challenging. I know folks up in the valley are really scratching their heads over what to do with the big interest in tile drainage now, and wondering how they should respond. So it's very, very challenging. And although I think trying to work at the watershed scale is commendable, I don't necessarily think that just because we do something at the watershed scale, it's inherently better if we don't really understand how the system works. I certainly think we need to continue to think along those lines. I'm just not sure
Question back there,
how it's
Gary.
going to play out.
Yes, Dr. Sands, you had a chart about prairie grass, cord, evapotranspiration, runoff, and flows. Crossed my mind that did you compare those on similarly drained soils, or for instance in the native landscape, you have a lot of ground that was too wet to support good prairie grass. We were more into the wetland species, and I realize there's a crossover there. But I think you shouldn't get the idea that this prairie grass was doing all this wonderful stuff in the native environment where a lot of instances it was too wet to start early in the spring, for instance.
Yeah, very, very good point. And that was not my work. That was some work that came out of Wisconsin. Those soils were identical soils. They were actually lysimeter studies, so they were small scale, highly controlled small scale studies of soil water movement. The interesting thing about the prairie versus the corn in that study was what they saw was that the dense mat of material that's at the base of the prairie was just an incredible sponge. And so it was able to soak up a lot of rainfall, and then that was available later for infiltration. And that's one of the things that contributed to sort of a more stable soil water condition under the prairie, and in general a wetter condition. But I agree with the assertion that we see all kinds of conditions on the landscape, wetter conditions, drier conditions that are more conducive to one species versus another. And again, that wasn't to suggest that we kind of need to dial things back and do it a different way. It was only to suggest that the landscape is, there are a complex set of changes that have unfolded over time.
Jerry, question?
Where do you draw, or where do you decide to use a buffer strip on a dredge ditch? Most dredge ditches the banks go up a little bit, there's a slope there, versus rivers and creeks, I can see that, but we're on a dredge ditch, where do you draw the line on that?
That's a challenge, isn't it? And that is one of the inherent issues when you have, let's say, a regulation that says thou shalt put a buffer along every ditch. We know that because of our spoils banks, we don't get a lot of surface flow in some of those areas. And when you don't have the surface flow moving through it, the point of the whole buffer is kind of moot. So
There's another question back there.
Yes, one of your earlier slides said that something to the effect that tile drainage decreases surface runoff. And I guess I wonder if you could just explain that a little better, because it seems to me that as
so
you're
we're
lowering the water table, it's going up, it's going into, it's going somewhere.
Yeah, so
Where's
the
the
question
water
was, I made a statement that in general tile drainage decreases surface runoff, and maybe I want to elaborate a little more on that because the water's got to go somewhere. So I'm talking about surface drainage. That's water that doesn't have a chance to infiltrate. It runs off the surface, gets to a ditch, and then finds its way to a stream, versus water that has a chance to infiltrate, get to a tile drain, and then move off the landscape in that way. So in a tile drain landscape, again, not for every rainfall event, not for every landscape, not for every scenario, but in general, again, we're talking in generalities here. In general, a field that's poorly drained but has now tile drainage, you have a greater opportunity for infiltration. So you'll get less surface runoff on that field than you would have had otherwise if you didn't have the tile drains there. So you get more water going down through the tile instead of running off the ground surface. And so that's what I mean by in general, where we have tile drainage, we have greater infiltration and less surface runoff in general. And I can see the look on your face. I haven't convinced you yet, but I'd be happy to talk with you more about that. We're talking in general terms here now.
Thank you, Jeff.